we have been discussing signals, and in my last session, I showed you how to handle signals if when they occur. So today we shall see in little more detail how SIG action can be used. Before that, Vinod has missed a lot of classes. A quick recap of what we have been doing. So signal, as you know, is a asynchronous event. It can occur at any time, and it is generated either by a software or by a hardware. So there are 31 different signals, and they are numbered from 1 to 31. And if when the signals occur, if not masked, it will be delivered to the process. So this is your process, which is executing some instruction. In the middle of this, if a signal arrives, then the process will handle these signals in three different ways. One is let some default action take place. So the default action is defined for all the signals here. If you see the third column here for all the signals, for example, if signal interrupt occurs, we have seen this. If I say Control C, the program terminates. If you have not set up any signal handler, the program simply terminates. Similarly, SIG quit, if this signal occurs, that is caused due to control backslash, then apart from terminating the program, the memory image of the program will be dumped on the disk. So core dump will happen. Using this core dump, you can analyze what went wrong when this signal occurred. Okay. So
I'm just asking one more question.
yeah,
This control plus backslash is there.
yeah.
So in Unix and both in Windows platform, the same thing will be happen or
If operating systems are POSIX compliant,
okay.
so there is a standard for operating system called
Yes, yes.
POSIX. You are aware of this. So if Windows is compliant with POSIX, in most cases yes, then this is what will happen.
Okay.
Okay.
Okay. Fine.
So that is why that standard is defined, and if any operating system conforms to this standard, all these definitions will work for that operating system.
Okay. Understood, sir.
So every signal has three disposition. One is let some default action take place, or you can set up a signal handler. Okay, so you can decide what will happen when the signal occurs. So you can put out a message or carry out some cleanup action and then close the program. So signal handlers you have to set up. The third is ignore the signal. So ignoring is simply ignore. It means even if the signal has occurred, the program behaves as if the signal has not occurred. Okay. So when you are in middle of some critical operation, this is the best thing to do. You simply ignore the signal. However, in most cases, you have to handle the signals. So we shall see through a couple of programs how all this is done. And in between the signal and the process, there is a mask. So mask is nothing but a bit pattern. Okay, you think of this as some 32-bit number. Because there are 32 different signals, you can think of each one of these used for blocking the signal. So if this is empty, it means the signal, this pattern is called as signal set. It means it's just one 32-bit number. Of course, you can ignore 1 bit for sign. You can ignore this, but remaining 0 to 30 bits are for defining the masks for the signal. So if you initially when you define a signal set, you have to make it empty. It means all bits will be 0. It means all signals are allowed to be passed to the process, so no masking. However, if you want to set up a signal mask, you have to add the signal to the set. It means if I want to mask signal interrupt, there will be one particular bit you have to set it to 1. Okay, so instead of you going and finding the bit where 1 has to be done, you simply have to call a function to add the signal to the set, automatically that particular bit will be set to 1, and you have to call one process, one API called as SIG proc mask. So there is a API calling this will ensure that the mask is in place, and if the signal occurs, the signal is recorded that it has occurred but not delivered to the process. Why this is done? Because if I remove the mask at some later point in my program, suppose you have set a mask here at this point in time, and you are doing some critical thing, and once you are done with that you want to unmask, so it is possible to reset this back to 0, and if the signal is pending, okay, it has occurred but not delivered, but if the mask is removed, then the pending signal will be again delivered to the process. So after unmasking, the signal again will be delivered to the process, and the process, if it has set up a signal handler, that handler will run. Okay, so this is a very fine control over the way signals are handled in a process. Okay, so as you can see, this is a long list of all the different signals. You should be aware of some of the very important signals. For example, sig ill. If you execute any illegal instruction, then this signal will occur. Now, what all might be wondering, when I'm using my machine, why would I execute an illegal instruction? Okay, now imagine a scenario. You have compiled your C program on an AMD machine. Its instruction set is different, and you have an executable generated which contains machine codes of AMD. And if you bring that program on an Intel machine and try to run, obviously all the instructions will be illegal. So it doesn't allow your program to run, and SIGIL instruction, SIGIL signal will be generated. And this is where you can report that the program is compiled elsewhere or contains some illegal operations. Okay, so this is very helpful. Similarly, signal abort. In the middle of a program, you can generate a abort signal. For example, you are doing some transaction. A C program is doing some transaction with the database, and there some some exception will occur, that there is not enough balance or there are not enough seats to reserve. You want to abort the process, so you call this sig abort, and this will be delivered to the process. And if you have left default action, then the core will be dumped and the process will terminate. Okay, signal FPE. This is a signal which is generated whenever you do some floating point exception, like divide by 0 or something. All right, so you should be aware of few of the signals which are listed here. Sig kill, we have seen at the shell prompt we do a kill command. So what that kill command is doing is basically it is generating a kill signal to the process. So as you can see, sig kill cannot be ignored. Okay, immediately it will terminate the process, and you cannot set up a signal handler for this, cannot be caught. Okay, so there are two signals for which you cannot set up a signal handler, or even if you set up one, it is immaterial, it will terminate. So sig kill is one, sig stop is another. So these are the two signals which cannot be masked and cannot be handled. They will be delivered to the process and default action will happen. Okay, so
sir, how to generate sig stop? Is there any keyword or
see,
what
there is one function called as raise.
raise?
Here if you set up sig stop,
Okay.
automatically sig stop signal will be generated to the same process where you are calling this.
Okay. And how to resume it after that?
No, here if you say sig stop, okay, you cannot it cannot be caught, you cannot set up a signal handler.
Okay.
It will pause the process here
Okay.
effectively. Pause the execution. On the other hand, if you say sig kill, the process will terminate and core will be dumped.
Okay.
Immediate forced termination. I will show you this raise, how to do that in a program.
Yeah.
I'm just listing out what all signals which are there. Okay, so a lot of big list of signals are there. They are very crucial in the execution of many of the processes. So if whenever a background process tries to write to something to the terminal, background processes will not have any connection to the terminal. If they accidentally try to do that, SIGTTOU will be generated. Okay, and similarly, if a background process try to read from the keyboard, then SIGTTIN will be generated. Okay, so SIG stop can also be generated using Control Z. Okay, this is again terminal stop. From the shell prompt you can stop a process. So these are some of the signals which are part of the signal set. For example, the last one is 6sys. Again core dump will happen, bad system call. If you try to write anything as system call and execute, it will generate the 6sys signal to the process and process terminates. So this is a very robust system which will make sure that nothing illegal or nothing exceptional will happen when you run the program. So all cases will be taken care of with the help of signals. So that is why study of signals is very, very important. So in my last program, I showed you how to set up a signal handler. A simple signal handler will contain one function. You can give any name. Only thing is return type should be void and the argument should be of type int. And this indicates the number of the signal which is listed in this list here. So every signal has a number. You can see SIG stop is 20 and SIG alarm is 14. Okay, 6sys is 31, like that. So if you want to print that number, you can do it here. And within the process, you have to set up a signal handler. It means you have to notify to the operating system that this is the handler for the signal if it occurs. For example, there is a SIG hub signal. So you have to call the API signal, pass the signal name and the signal handler name here. So 2 arguments to the signal function. And within this you can put in a loop and pause it. Okay, so pause is a API which will stop the process, waits for the signal to occur. If and all signal occurs, then it will go to the handler here. And since you want the program to continue indefinitely, you put it in a loop. If you want to exit after first occurrence of the signal, then remove this while loop. And the way to generate SIG hub signal is use kill command -HUP and the process ID. So this process will be running continuously. First note down its process ID and execute kill command with -HUP option. This will generate SIG hub signal for this process. Now using signal function to set up a signal handler, there are 2 problems. One is this is not a POSIX standard. Okay, and on one machine it may work, on another machine it may not work. Okay, so this is discouraged. You should not be using simple signal function to set up the signal handlers. And second is it is the signal may repeatedly be generated for the process. So this leads to what is called as race condition. Because for example, when you set up a signal handler, if you go into the signal handler, again signal occurs, then what will happen? Again this will execute. Okay, so repeatedly the same signal handler keeps running if this particular signal function is used. So better option would be use SIG action API, which is a more advanced version and more stable version than the function signal. So we shall see how this SIG action to be used. And for this SIG action API to use, you must understand the structure of a SIG action data structure here. So as you can see, struct SIG action, it contains 4 parts here. First one is the signature of the signal handler. So if you are using basic signal handler with only printing the signal number, then use this first option, that is provide a signal handler address here. we shall see how to do this. But suppose if you want something more information about the signal, like who caused the signal to occur and what was the reason for the signal occurrence, then there is a second function called as sig action, where there are three arguments. The first one is the signal number, second is the signal info. Using this, you can know which signal caused the error and what was the error and what is the source of this signal, whether it is caused by the kernel or caused by the another process or caused by the shell. Okay, so you can know all that. And there is a third argument which is a generic pointer. Using this, you can get access to all the CPU registers, stack pointers, program counters, etc. For debugging purpose. Okay, so this we will not be using in our program. We will be confining ourselves to the second argument, siginfo underscore t. And if the signal occurs when it is in the handler, if you want to mask, then you have a SA mask as the third argument. So remember, masking the signal in the process is different from masking the signal in the handler. Okay, so if you want to mask the signal when you are in the handler, then this sig mask, which is part of sig action, should be made use. Okay, and the last argument is SA flags. This will allow you to do more things, like for example, in the middle of a read from a file, if a signal occurs, what will happen after the handler is executed? Will the process continue reading the file or not? Decided by this SA flag. If you use SA restart, then the process will resume and start reading the file from where it interrupted. But if this is not set, the process will terminate. Okay, so if you want a continuation of a system API like read, write, etc., then this is a better option. And third one, if you want additional information about the process which caused the signal to occur or reason why the signal occurred, then you should combine this with sig info. Okay. So we'll see all this in demonstration, how this SA flag can be used to derive more information about the cause of the signal whenever it occurs. Okay, so I have given you an overview of what signals are, what different signals are there, what will happen when the default action takes place, and you have an option to ignore the signal also. And if you have set up a signal handler, the signal handler program will run. Okay, and there are two ways of setting up signal handlers. One is using signal API and second is the sig action. Okay, so let's see now with the programs how all these things play out. I will start with very simple.
Sir, you will share that the list of signals post the class, right?
Which one?
The one you were sharing.
That 32 signals.
Yeah,
Oh,
signals.
this list you wanted, huh?
Yes.
Yeah, I'll pass it on to you. Okay. Now, let us begin with very simple program. From here on, we'll see how to set up signal handler and how to test them. You must be including the signal.h file for the use of signal API here, and UniSTD for the pause. Okay, so I have set up a signal handler for interrupt signal, that is control C, and the handler function you have to define it here. The return type should be void, and you should give the same name as you have given it here, signal underscore handler, and the argument to this is the signal number. And within the body of this, you do what is needed. Handling the signal is reporting that such and such signal has happened, and if you have opened some files or if you have used some system resources, you clean up all that and then terminate the process. So that can be the work of a signal handler. So here I will simply print signal number. I am signal handler received signal number so if I compile the program, so it is waiting for the signal to occur. If I say Control C, I am signal handler received signal number 2, and if you go and see here, signal number 2 is SIGINT. Okay, and if I press sig control backslash, it should display signal number 3. Of course, for that you have to change the program to make it sig quit here. Is the spelling correct? Sig quit, yeah.
In the same, actually, can we register more than one signal in the same?
Yeah, you can have more than one signal handler, and you have to call the signal function with different signal numbers here.
Different signal number, but the same destination.
No, the handler definition will be different, no, for different
Yeah.
signals.
Okay.
Control backslash. If I say control backslash, see signal received is number 3. Quit is number 3. So this is how I can set up a signal handler and handle it. Okay, but what if I want to ignore the signal? Okay, so let's see that nano sig ignore. Yeah. Now I have a handler here, and for signal interrupt I want to ignore this signal, and if I type Control C and see what happens, actually it will not respond. Okay, so let's see if I compile this. Sorry, minus O signal, can give any name. So as you can see, if I say Control C, nothing is happening because you are ignoring the signal. Okay, you type any number of times, only one signal, it will be recorded only once, but it will not be delivered because it is ignored completely. Now the only way to kill this process is type kill command in another terminal. So here first I have to check the PID of the process which is running using -xj command. As you can see, .si is running with PID equal to 1890. So I have to pass kill command 1890. This will send sig kill command, and even if it has ignored, that ignore will be overridden and it will kill the process. Now if I come back to my terminal, you will see that terminated. Okay, so since you ignored the signals SIGINT, which can be ignored, but it cannot ignore the sig kill signal which is caused by this kill command here, and the process terminated. Now if I check the process list, that .si is gone. Okay, so this is how you can ignore this thing. Now another program to see what happens if I let default action to take place. So there is a sig default. Now here what I am doing is I have a signal handler for signal interrupt, and I have mentioned instead of signal handler here I am saying sig default. Okay, and if I say Control C, the default action will take place, and if you go back and see for SIGINT, default action is terminate, so process will terminate. So let's see if this gcc sigdef dot c minus o sigdef. Okay, this should be sig. Okay, type Control C and watch what happens. If I say Control C, default action is terminate the process, so it will come out. It did not go to the signal handler. Okay, now these are very simplistic signal handlers, and one problem with signal, as I told you, it is not reliable and not portable also. So we need to look at sig action. Now let me check what is this simple 2.c. Now if a process wants to generate a signal for itself using alarm signal, which I told you, Vinod, that we'll take up this one first. Now signal sig alarm, and we have to set up a signal handler, and if I want signal alarm to happen, you just call alarm function and specify after what delay, 2-second delay. So let's see how this works. Void signal handler int signal number printf I am signal handler received signal number equal to %d. Okay, so what should happen is when you run the program, it should wait for 2 seconds, and after that this message should get displayed. So gcc simple1.c -o s1. See, for 2 seconds nothing happens, and then I am signal handler received signal number 14. So signal number 14, if you go through this list, it is sig alarm, and the result is terminate the process. So you see that process got terminated when the signal occurred. Okay. Now this is about this sig alarm, and now if you look at sig action, to use okay, before that sig CHLD. Now this is one very important signal you must be aware of. A child can send a signal to the parent, and that signal is sig CHLD. This will automatically happen whenever the child terminates. Okay. Now to demonstrate this, I have taken a PID variable here and fork the process. So when you fork, the child process will be created, and within the child process space, I have told you some time back, if PID value is 0, that part of the code corresponds to the child process, and fork will return twice, once in the parent, once in the child. So in the child, I am just saying I am child exiting and exit 0. And what the parent will do, it will simply wait until sig CHLD will be generated. And since you have set up a signal handler here, this message will also be displayed. Okay. So if you want some delay in between, then you can sleep here for some time. gcc simple2 -o s2. So as you can see, I am child, and after 2 seconds I am signal handler caught signal number 17. Okay, if you see signal number 17 here, it is sig CHLD. The default action is ignore. That is, in a normal situation, if you have not set up any handler, even if child terminates, nothing happens to the parent. Okay, so that you must be aware of. Now let us see simple 3.c. Okay, let's see how to use sig action, which is more robust and more portable. For the same sig CHLD, how I should have set up the signal handler in this case. Now this sig action is a structure, and it has 4 parts. first part is SA handler. So SA dot SA handler equal to signal handler. So I should set up signal handler here. Okay, and then SA flags. If you don't want any restart or anything, you can simply put it 0. So the default value is 0 here, and then you have to call the API SIG action. So just observe the name of the API is also same as the structure SIG action. Okay, so don't get confused. SIG action is name of structure also, and SIG action is name of API also. Okay, the first argument is the signal name for which you want to set up a handler and pass the address of the SA structure. And third argument is null, or it can be whatever is the current disposition the signal may have. You want to save SA old and pass as the third argument. The other day I had some confusion regarding this, so I got it clarified. The third argument is the current disposition the signal might have. For example, default action may be there for that signal handler, so that will be maintained in this. So this will be useful if you are setting up, if you are calling SIG action many times, and whatever was the old SA detail that you want to keep, that can be kept in SA old. It should be SA old here. But if you don't want to remember what was the disposition for the signal before, you can put null. Okay, so in a very simplistic scenario, SIG action third argument will be null. Okay, and if you want to wait for the signal to occur, okay, of course 6 CHLD will not happen here, because you have to first thing is you have to create a process, because there is you need to write the program for the same. Go to 0, then you can just exit from here, so that this will cause the 6 CHLD to be delivered to the parent, and the parent can wait for the signal to occur. Okay, so we have set up the signal handler. It will only print the signal number. If you want something more, you can write 6 CHLD like this. Okay, let's see what happens when I execute this program. As you can see, immediately 6 CHLD will come here, because the child executes, it will simply exit. Okay, and it will show which signal occurred. So SIG action is a more robust mechanism to set up signal handlers, and you should be using SIG action more than the regular signal API. Now, is that the only use of SIG action? Okay, so SIG action can be used for more detailed purpose. So let's see another program where I can use signal action API to display more information about signals when they occur. So for this, as before, you have to use struct SIG action SA, and instead of signal SA signal handler here, you have to say SIG action. Now there is a difference between whenever you use SIG SA flags with SIG info as one of the defined constant here, you must be using SA sig action, not signal handler. Okay, it should be sig action. What happened? Yeah. Now let's set up the signal handler. But this time when you set up signal handler, okay, it cannot be the basic signal handler that we handled earlier. Signal handler. Just observe the change that comes in. The first argument is signal number only, but here sig info underscore t will come as the second argument, and it is a pointer. This is again a structure, basically has many subparts. We shall see what all it has. And the last argument is a generic pointer and named usually as uContext. It means the user process context, which contains the register, variable, values, the stack pointer, program counter, and all that. So you can ignore this for now. Now if I want to print the details about the signal, so first thing is signal number equal to %d, and if you want to print the process ID which caused the signal to occur, you can say PID equal to %d, and if you want to display reason, the first thing is signal number, second is info underscore arrow, this should be SI PID. This is a member of the structure variable, and then info underscore SI there is one more, let me check that. Okay, let me check with ChatGPT. I forgot that structure. Show sig info underscore t details. Okay. Yeah, it is SI signal number, SI error number, SI code. Okay, it is SI code. Okay, so we are now able to display far more information than what is possible with normal signal handler. Okay, along with signal number, I can display who caused the signal to occur and what was the reason for it. Okay, and then down here, the program remains the same. You have to call sig action, and within the signal handler, I want the mask should be clear. So sig empty set SA mask should be done, and then you have the child process exiting before, and here you can terminate the process through exit, or you can raise a signal here, sig kill. Now let's keep it like this and see what happens. CCC sig more dot c minus o. Okay, so just observe what happens. The child is killed, and the signal number sig kill is 17, and this process only killed it. The PID of the process which caused the signal is listed, and reason is 2. Okay, so there are numbers. If it is generated by the kernel, the reason will be 1, Okay, and if it is caused by the process, it will be 2 like that. Okay, so for instance, if I edit this program and instead of sig kill, if I exit, let's see the difference between, yeah, as you can see, signal number again is 17. It is PID is a process, and reason is 1 now, because exit will be generated by the kernel, okay, not by the process. So this number will tell you who caused the signal to occur. So that is about the usage of the siginfo underscore t. So far so good. Any doubts?
Actually, in the SIG, in the fork, we have just had added the this thing, right? Can we sleep for some times and can we just see what is the process ID of that child forked kind of thing?
You want to sleep for some time here?
Sleep for 10 seconds. In the next new this thing, we can just say like, okay,
Here
what is the process ID of the child kind of
it
thing?
will remain the same. I mean, there should not be any difference, right? Only thing, after some delay, the 6CHID will be delivered.
Yes.
Yeah. Getting killed. Now,
In the parallel thing, I just wanted to check what is the process ID of the.
yeah, process ID will be different this time, because every time a program runs.
Meaning I just want to see like if you UPS icon this thing, then it will give you the exact process ID of the child as well, right?
Yeah, yeah.
One,
So you wanted to check whether this was correct. Then you have to open up another terminal and check.
yeah, that is what I was
Okay, okay. You want that? Huh?
Yeah.
Let's see 1 minute.
That is why I was just asking for sleep
Okay.
for 10 seconds and verify the new terminal and we'll say
Okay, let's see. More time is needed. So SM is running 2014.
2014 is. 2014 or 2013?
Yeah.
Yeah.
So the child PID came.
Yes. Okay. Fine, sir.
Now, how to mask the signal? So that part remains. So for that, I have a sigmask.c here. So first thing is you have to define a signal set. There is a structure defined sig set t. I don't know, it's not structure, it's basically a unsigned integer, 32-bit number, and you have to define my mask. Okay, so first thing is you have to empty this set, sig empty set ampersand dot sa mask, and whichever signal you want to mask, that has to be added to the process. So here sig add set ampersand sa dot sa mask comma sig chld. I want to mask chld, 6chld, let us say. So this is a setup, that is you have marked that this signal should be masked, but actual masking is done by a function called as sig proc mask. And first argument is sig block, and third is the old mask you want to retain. You can pass another variable ampersand old mask, or just keep it null. So what happens now is even if 6chld handler your setup, as before, and you're causing that signal to occur by sending kill process here, or you're just exiting. Okay, so what should happen is signal is masked, so no signal handler will happen. Even though child has terminated, then after 2 seconds you want to unmask the signal. So the way to unmask the signal is you have to again say sig pros mask sig unblock here and ampersand my mask. So what will happen is the signal which has occurred before is registered. Moment to unmask, it will occur and you will see this signal handler will execute, showing which signal was caught and from where it came and all that. So let's see whether it goes through. GCC sigmask dot c minus o. Okay. That happened in quick succession. We should have given some delay. Okay, so 1 minute. Seconds. Is that syntax correct? Sig block, sig my mask. Sig empty set ampersand. This will clear the signal set. Sig add set. Sig chld. This will block the signal, and we are setting up the signal handler here. Process is created. Okay. It's immediately unmasking. Just a minute. Sig proc mask.
After exit, pause will not be executed, right?
Yeah, here it is not required. I think so. It should wait for the signal to occur. No, this is masked here. Sig proc mask. Handler is set up. Why the sleep is not getting executed?
Sleep is getting executed.
No, it should wait for some time. No, immediately it is coming out. No, signal handler is getting executed. Actually, this signal handler should not run.
Right.
Okay, so where things are going wrong? SA flags, SA restart SIGINFO. Is the signal name correct? Sig CHLD?
Yeah, CHID is
Sig CHLD, that is correct. 6HLD SIG block my mask. Is it causing this mask to be cleared? Let us close this and see. Oh, this pause should be here. Let us see. AUC pause. No, pause. Let's check. It is not getting masked only. What is the effect of this masking? One minute, I'll just check with ChatGPT what it says. See, whenever you get stuck, you can ask ChatGPT for help, because very minor mistake you won't have done. So these subtle mistakes you cannot figure out. Sig mask is sig pop mask is not working. Check this. Okay. Sig my mask is never initialized. Okay, what I should have done? Sig empty set I should have used. Have you done that? Okay, so one
You commented.
yeah, I have commented this out. That is the problem.
No, but before commenting as well, it was the
the
same
same
thing.
thing.
No, sig empty set should be done, and then you should add the signal for masking. So let's see whether this will solve the problem. Which should the order should be different.
Yes, it is saying like first.
This should be done first.
I think
Empty set, add
add
set.
set.
One mistake which I have done is here I should have emptied sig empty set with my mask also. This should be emptied and then you should add the mask. Here there is a mistake. I was getting confused with the essay mask and this my mask. My mask should be made empty and then you should add the signal for masking and then sig proc mask and then sig action. Yeah, I think so now it should
I
be.
think we can do the structure. We are not zeroing it out. We have to
Yeah.
zero it out before
Let's
doing
see,
this.
let's see whether it works now. Yeah, now unmasked and then the signal should be delivered. No? But it is not getting delivered. Masking is done now.
I
I
think
think
pause
pause
you
you
should
should
remove. I
remove. I
think
think
pause.
pause.
Yeah, this pause should be removed.
Yes.
Yes.
Yes. Yeah, now it worked. Okay. So initially it was masked. Even though child got killed, 6 CHD generated, but it was kept pending. And only after you unmasked, the signal handler executed with code signal number, and this came from 2081. So,
Sir,
Sir,
actually,
actually,
when
when
we
we
have
have
added
added
the
the
this
this
thing
thing
struct,
struct,
right?
right?
It
It
said
said
that
that
my
my
mask
mask
and
and the
my
my
mask
mask
struct we
struct we
have
have
defined it,
defined it,
right?
right?
So
So
empty
empty
set,
set,
empty
empty
set
set
will
will
actually
actually
reset
reset
the
the
numbers
numbers
in
in
that
that
one,
one,
yeah,
meaning
meaning
whatever the
whatever the
entries are
entries are
there in
there in
that
that
struct,
struct,
or
or
yeah,
uh,
initially it will contain some garbage value.
so
so
can we
can we
have
have
made
made
B0,
B0,
meaning
meaning
binary
binary
zero, we
0, we
just
just
make
make
B0
B0
ourselves,
ourselves,
or
or
else
else
my
my
mask is
mask is
equal
equal
to
No, no, no,
to
no.
DD, as in this
See,
would
we
happen.
don't know whether this is a 32-bit number or what it is. Okay.
No, no,
No, no.
what I'm
What I'm
So
asking is,
asking is
you have to call sig empty set to clear all the bits.
right,
right,
right.
right.
What
What
I'm
I'm
just
just
asking is
asking is
like,
like
Ah.
if
if
680
680
my
my
mask is
mask is
there,
there,
okay,
okay,
and
and
after
after
that
that
my
my
mask is
mask is
equal to
equal to
within the
within the
flower
flower
bracket
bracket
0.
0.
If we
If we
do
do
that, then
that,
it
then
will
it will
zero out
zero
all
out
the
all the
things,
things,
right?
right?
So that
So
is
that
what
is
I
what
was
I was
just
just
checking.
checking.
Or
Or
else we
else we
can
can
just say
just say
like
like
B0
B0
and
and
clear out
clear
all
out
the
all the
memory,
memory
or
or
Well, that could be done if you are
uh-huh.
using B0, it will clear off all the bits. Okay.
Mm-hmm.
mhm,
But the standard way to do that is use the
Sig
sig
empty
empty
set.
library
set.
So
function
that
or
So
the
whatever
that
system
the
what the
function.
reset
reset
value
value
that,
Yeah.
that
that
might have
might have
defined,
defined,
that will
that will
be
be
resetted,
resetted,
right?
right?
Okay. And then whichever signal you want to block now, that should be added to the set now. For
Okay.
example, in the same set, if you wanted to add interrupt also,
Mm.
Mm.
so sig add set ampersand my mask comma sigint. So now
Mm.
interrupt will also be blocked.
So we
So
have
we
to
have to
kill
kill
from the
from the
other
other
process,
Yeah.
process
or
or
control
control
Okay.
backslash.
So
backslash.
now if I execute, even if I do control C, nothing happens. Okay.
Mm.
But after unmasking, this control C will be delivered and default action is terminate.
Right.
Right.
6 CHAD will be ignored because
Yeah,
process only
because
has
of the
Because the
gone.
priority.
priority.
Okay, so because of the priority. So it's a very interesting topic to learn, provided you give some time and experiment. Because things are slightly more complicated here because you have to understand what is this sig empty set I am doing here. Okay, this I have to do because in the signal handler, if the same signal appears, I don't want to ignore that or uh, mask that. So that sig empty set should be done using SA mask. This is for clearing the mask for the signals when you are in the handler. And this my mask variable is when you are in this process in the main function. Okay, so there are two different things. Okay, so you have to do empty set two times. One is for the signal handler empty mask and one for the process empty mask, and then add the flags that you want to mask and call sig proc mask to block it and let the signal handler be set up and let the signal happen. If the signal CHLD happens, it will be blocked anyway. So we have to wait until this step. After the sleep time, you want to unmask it. So again call sig proc mask with sig unblock as the first argument and then pass the same mask. Okay, so that the signal which you had added, they both will be unmasked and they will be delivered to the process.
Okay.
Okay.
Sir,
Sir,
actually in
actually in
SigProc
SigProc
mask we
mask
are
we are
unblocking,
unblocking,
right?
right?
So
So
can we
can we
empty
empty
set
set
before
before
that,
that,
meaning
meaning
SigProc
SigProc
mask,
mask,
before
before
SigProc
SigProc
mask, can
mask
we
can we
just
just
empty
empty
the
the
Sig
Sig
empty
empty
set
set
my
my
mask
mask Can we
Uh,
do that so that
no, no. Emptying the set will not actually unblock. You have to call SIG proc mask.
okay,
Okay,
yeah,
yeah,
because it
because
would
it
have
would have
registered
registered,
and then
and then
only it
only
will
it will
replace
replace
that
the
to
truth,
the
the
actual
actual
struct.
struct.
I
Yeah, I
got it.
got it.
But
But
actually, if
actually, if
we
we
do
do
that,
that,
then
then
it
it
won't
won't
be
be
any
any
effect on
effect
that
on
one,
that
right?
one, right?
My
My
mask,
mask,
meaning
meaning,
You are saying unblock. No, which signal to unblock?
no,
no,
I
I
just
just
want
want
to
to
see
see
what I'm
what I'm
saying is
saying
sig
is sig
empty
empty
set we
set we
have
have
done
done
above,
above,
right?
right?
Okay.
So
So
in
in
sig
sig
proc
proc
mask,
mask,
before
before
sig
sig
proc
proc
mask,
mask,
if
if
we
we
do
do
empty
empty
set
set
against the
again the
my
my
mask,
mask.
Okay, let's see. I'll experiment with what you are saying. My mask. This is what you want to do.
right,
Right, right,
empty
empty
set,
set.
yes.
Yes.
Then do what?
Um,
Um,
uh,
uh,
then
then
Should it
okay,
be block or unblock?
uh,
no,
no,
can you
can you
just
just
It should be blocked now because this mask
yes,
is
yes, yes,
empty. Nothing will
right,
be
right,
blocked. No.
right,
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 and
and
then
then
we
It should work.
again
again
It should work
if
the
if
same
it
way. Let us see whether it does.
mm,
No. Sig. I made a.
sig
sig
empty
empty
set.
set.
Okay. Yeah.
No, CHLD
CHLD
also
also
not
not
executed.
executed.
CHLD is not executed because
Sigin
Sigin
we
we
have
have
registered.
registered.
this emptying thing will not work like that.
Okay,
Okay,
You have to go the usual way. You have to
okay,
unblock it
okay.
okay.
Yeah,
because
Yeah,
we have
we have
unblocked.
unblocked.
unblock only will work, and you should not do this.
Okay.
Okay.
Anyway, you understood the whole process, right?
Yeah,
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 So,
yeah.
yeah.
masking is very much useful because when you are in the middle of some critical operations, you don't want any signal to disturb you. So, you
Right.
mask them. And once you are done with what you are doing, then you unmask it.
Unmasked.
Unmasked.
Yes.
Yes.
Okay. So, we shall see in our next session about files now. We are done with processes, process related signals, daemons, etc. Now it is time to shift over to file system. How actually the file system is maintained using the kernel data structures, and what happens when you create a file, when you destroy a file, when you modify the file content. That part we shall see in our next session. All right?
Okay.
Okay.
Okay then.